Okay, so welcome back. We are very happy to have Kausik Ghosh in the afternoon session. He will tell us about defects in random field models, lessons from Parisi Sourlas.
Okay. So thank you very much. Thanks the organizers, especially Apratim and Victorco, for organizing this beautiful conference and giving me the opportunity to talk about our recent work. So this is about introducing some defects in random field models, and this story has got quite a bit of interest due to actually work of Slava, Apratim, and Emilio. They kind of understood some very long-standing problem in this field when there is no defect. And we kind of try to understand how this kind of setup can be extended in presence of defects, and if we can learn something about it. So that's what I will tell you about. And okay, so I will briefly tell about the usual story of Parisi Sourlas, because that's very important in this construction. I mean, that's how we thought about how it can be extended for defect case. So as you can see that random field plays an important role here for realizing Parisi-Sourlas type of supersymmetry. I mean, that's a physical context where Parisi-Sourlas type of supersymmetry appears naturally. But Parisi-Sourlas on its own can exist. And whenever you have such a supersymmetry, there will be dimensional reduction, which I will explain what do I mean by dimensional reduction. So the usual story is, so you have a Hamiltonian like on the lattice with visible with the Ising-like interaction. And then we add a position-dependent magnetic field to it. And that has some dramatic consequence in this story. Like we know that if this term is not there, then the phase diagram is that if we are below 4 dimension, then there is a non-trivial IR fixed point, and we know that part. But as soon as we add some impurity like this, it seems like for example, one of the dramatic consequences is that the upper critical dimension goes to 6 instead of 4. So now we can have the phase transitions for d greater equal to 3, but up to 6 dimension. But even more dramatic consequence is that people. So this model was proposed in 1975 by MD and Ma, and then in 1976 by a paper by the same group of people, also by Aharoni. I mean, they wrote a paper together where they showed that if I consider this model in d dimension, then actually it turns out that the critical exponents gets mapped to a usual without any impurities, like just the usual Ising model, but in d minus 2 dimension. So that's quite surprising. Like why a theory which has this random. Okay. So one thing I didn't say, like usually this field will be treated as a random field. So this is like a quench disorder. So why this disordered Ising model flows to some fixed point, and then that fixed point has the same critical exponent as the usual Ising model without any disorder in d minus 2 dimension. So that was the surprise. And you can see that there is a problem because this model has a phase transition at t equal to 3. On the other hand, here it's saying that there should be a phase transition at 1. So it can't be true, and something should go wrong. And that was the puzzle actually that Apratim and Slava and they kind of.
The HR is a center with zero.
Yes. Oh, sorry. Yeah, I didn't say anything about that. So indeed, you mean the mean value? Yes,
Yeah.
that's zero. Yes. Yeah, I will save it. So is there any physical reason to?
Why the direction goes to six instead of four?
Indeed, it's because you know in the so I will not say so show exact derivation, but the point is if you we have to do some replica trick for this and do the field theory, and then when we look at the 5-4 interaction term, there is so it's a coupled replica coupled like term, and when you try to find the propagator, you will see that it's not actually a single operator, but it's in a CFT language, it behaves like there are multiple operators. And the lowest dimension that appears there, if you try to compute by the argument of marginality, that what should be the upper critical dimension, you will see that it's D equal to 6. So it's an artifact from a lattice point of view.
And it direct side, why should
No, I think this type of arguments we have to do it close to fixed point and in the field theory language, right? Because yeah, we are talking about artifacts. I don't know how to talk about this. But I guess close to fixed point, we are assuming that it's given by a continuum field theory, and then you can do the usual trick and see what's the dimension of the 5-4 operator that you have. And in presence of this, you will see that the dimension is not what we see usually. It's not D-4, it's D-6. So okay, okay. So let me say that again. So there is a random hill model, and it showed that in these people in 1976 they observed that there is a link match between this model, critical exponent of this model in D dimension, and usualizing model in D-2 dimension. Then in 1979, Parisi Sourlas wrote their famous paper where they showed, where they say that okay, we can forget about this model, but we can write down some supersymmetric theory, and they showed that in that theory, perturbatively to all orders, the diagrams match exactly that the D-dimensional. If you work in D dimension and if you draw all the Feynman diagrams, you will see that they get mapped to the D-2 dimensional Feynman diagram that you will do for the usual Ising model. So therefore, it's not so therefore there is some sort of a supersymmetry emerging around the fixed point, because of which this dimensional reduction is happening.
So this happens after you have averaged over age.
Yes, the whole computation will be done after average.
And the D-2, you don't have any age.
No, there is no age. There is just this term. Okay.
If you had it, there would be no age.
And this prevalence is at the level of
Critical exponent correlation functions with some condition that has to. Yeah, I will come to it. What's the exact statement?
and we call it duality.
Yeah, it's PS. I mean, I think. Oh.
Yes, I don't know how to.
Yes.
Yeah, actually, it's locked here also.
No, you can.
Yeah.
Okay, anyway, I will continue.
It's on the board.
Yeah. So I will not show any detailed derivation or anything, but just write few expression maybe that would be just helpful for me to say what I want to say.
So the order parameter here is still the total time.
Yes,
Yeah.
yeah,
This is the expectation.
yes, we are measuring the magnetic moment that will be. Okay, so the close to the fixed point. So this model that I wrote down, they admit this usual, like, it's the continuum version of that model is. It's these have exponentials. And then we couple a field here, the magnetic field here. And of course, we have to compute the observable, and then it's this usual prescription is that so for a fixed stage, I can compute the observable. And then the idea is that we are going to treat this H as a random tail. And in I think the idea is that when the volume is very large, treating this as a random parameter is quite a good approximation. Real material we can be ways. Sorry. So it's time to make sure. Yeah. So okay. So all right. So okay. So then the point is that we are going to take this from a distribution, and usually it's taken to be Gaussian distribution. So we are going to average over those different configuration. We are going to average over there. So essentially, my averaged. So this is some probability distribution that we choose. And that's my disorder averaged observable. So these are the things that we are interested in. But then the usual problem is that it's not really super important, but I have to say something that why we need to go to this kind of like I will come to that. But the point is here you can say like this computation is very hard because there is a ZH sitting in downstairs and we want to take a average of a different choice of H here. So this computation is very hard. So then the trick that people use is that we introduce this replica. So we introduce, so we have a field phi, but then we introduce, let's say phi I, where I runs from 2 to n. So we introduce this n copies of fields. So we can just think that we have n copies of this essentially. And then the idea would be that we want to, let's say we insert some 1 here, and that we can write, let's say ZH to the power n minus 1 by ZH to the power n minus 1. And here there was a ZH already. So at the end, we want to take n tends to 0. And that's the definition of my disorder averaged observable. So therefore, there is a ZH to the power n. One ZH factor will come from here. So this we set to 1. So then basically, this equation becomes e to the power minus s, let's call it n. So there is phi I and h. And this action is exactly this, just summing over these different phis. And that's. But then the good thing is that now, and the point is we should take the limit n tends to 0 at the end. So that's the definition of observable. And then what we can do is that we can integrate out this guy, because this guy, if I take PH to be Gaussian, then this is quadratic in H, so I can integrate out H. And that will introduce a term. So everything remains same, but that will, so this term will disappear, and there will be a term which will couple different replicas, and it will be something like sum over I phi I squared. So this H is essentially, so I chose some distribution with the width, so it's that. So let's say this is H squared over. So it's the width, strength of, and so we are assuming that Hx and Hy, so two impurities which are separated, I mean, they have no correlation. So Hx and Hy, this guy is delta x minus y. So there are no correlation between different impurities. So okay, so at the end we got some action which has the exact same form. There is only one term which couples the different replicas. That's the message. And I think this theory is good. I mean, we can compute all the observables, and of course, there is a subtle issue of taking limit n tends to 0, but okay, people know how to deal with them, and this works and so on. But for the purpose of Parisi Sourlas, it turns out that there is a different way to write down this action, which is important. Why it's important? So it's important because if you compute the like the correlation function of phi I and phi j, say in momentum space, you will find that this has some power like delta ij p squared plus because of that term which I said that it couples, you will see that it has a piece which also goes something like this. So you see, phi I is not a good primary operator in CFT language because it has two terms. We want to go to a basis where we write down some field theory and everything has a good, well-defined scaling dimension. Because then we can use our RG sense and we can do, I mean, that was super important to explain why there is no phase transition in D equal to 3, for example, where it should reduce to one-dimensional phase transition where there is no phase transition.
So, we started with this at least H.
Yes.
So that it's a good way to think of this as a coupling which that is space dependent,
Yes.
and then with that coupling, is it possible to do R3? So this is one question, and the next one is that when you in your replica, you just reduce it to this capital H, which is a constant. Then again, this is the coupling. Can you do RG? Then that is like a fixed coupling. Usually, we it a good way of
Do you mean the capital H?
capital H and small h both.
In what sense are you doing RG in terms of small h?
In terms of small h. Yeah.
I guess the answer is
It's a bit tricky because you see, I mean, because I mean, H is a position dependent
Yes.
thing, and that can be super complicated. Like to do any computation with that, because I think the idea behind doing this averaging is that whenever we compute some volume averaged observable, at the end of the day, it should not matter what choice of Hx I used. So whether treating it, I mean, you can of course treat it as a coupling and do RG, but I'm not sure. Because I think the idea is that the fixed point, close to the fixed point, I mean, it should be universal and, you know, you can choose some distribution and you average over this. Otherwise, I'm not sure. Yeah, if someone has any.
This knowledge, it's difficult to think of it in RG sense because you said these are independent Gaussian waves.
Yeah.
When you think of RG post-grade in space, so if these are independent Gaussian variables, if you post-grade it, the speed will just go to 0. Very quickly, right? So that
Yeah, but
no,
I was thinking probably
disordered average observables, right?
just to understand. I mean, do you mean like even if I average over and then can I think of, because if I average over,
average here. One is force training in real space when you do RG and you flow to long distances. The other is disorder averaging, which is not an RG. It's just
Yeah, it's not an
like a
RG. I
usual
agree.
field theory.
I agree, yes.
Yeah. So I guess she was talking about RG.
Okay, real space RG.
Whatever RG is. Yeah.
Yeah, I'm not doing any RG yet.
But probably since you have a m square phi square plus an h times phi, in a sense you can use a trick that m square phi square plus h phi. You can take a whole square
Yes.
and that will redefine your phi. In that sense, h will become another field, and it will introduce some coupling.
But it's important, I think, that we are never treating H as a field actually. Like
No.
we are not writing DH, for example.
No, not in that sense, but I'm saying, the first action you wrote, it's like the standard kinetic term of del phi square plus m square phi square plus a h times phi. So I can just play with that action, right? I can say that I'm having a x dependent
Yeah,
mass.
if P is 0, I think it can be,
Even if I don't want to touch V, let's say, I can absorb that h phi in a x dependent m square. By redefining the fields. And then your d phi will change accordingly and it will bring it. Okay. But I don't know if that answers our question.
but I think, I mean, at the end of the day, choice of HX should not matter. I think that's the viewpoint I'm taking here. So for the fixed, close to the fixed point, I mean, H should not behave like a relevant operator, or anything. Like it should just die out. I think.
H is not relevant. H is
No, if I treat the H as a coupling, what you're saying, I think that will not do any effect close to the fixed point. I mean, if anyone has anything better to say, we can say. Yeah. Okay. Indeed, and I was not doing any art. I was just translating from one form to other form by doing some complications.
Usually, if you have a completely random field in real space, it's hard to set up a null. You want to go to some other sort of combination so that you can set up a null, right? So that we can define momentum or something. So when you disorder average, you actually bring back translation.
So the thing that you wrote in terms of capital H, that helps.
Yeah, if you disorder average, you bring
Yeah.
back translation.
Thanks. Okay. So due to this problem, that these operators that appears in the action doesn't have well-defined scaling, we want to use this trick, which is due to Cardi. I can let it be. Like when I'm finished, I will. So we can go to a different basis of operators where operators have well-defined scale. That's the idea, and this is due to Cardi. He did this transformation. So the precise form is not important, but like. As you can see, so I goes from 2 to n. So I had n fields, so therefore when I rewrite it, I should have again n field, not more than that. So I have phi, I have omega, so they are 2, and there should be n minus 2 of them, but I can see that there are n minus 1 of them. So therefore you put a constraint that sum over chi is. So then we have n fields, and we want to go to this basis of phi omega and chi x. This is due to Cardi. And then if I write down the action, then if I write down the action, we will see that it takes some form, which is like. Fine. Yeah. So I will find something like this, and okay. So now if I try to compute the dimension, I mean they have well-defined dimension, and everything is good. Like if I compute the phi, omega, and pi I square dimension, I will find that. But moreover, actually, if you see, okay, so when I did this, actually there was an assumption. Actually, in in this transformation, you are generating more terms here, which we are throwing in because they are irrelevant. If I do the dimensional analysis, we will see that they are irrelevant, and they are those are the dangerous pieces, throwing away that extra piece, because they are irrelevant when t is close to 6. But they can become relevant when you come to a certain critical dimension. And that's basically the explanation why it fails there. But I didn't yet tell that what's the supersymmetry here. So to see the supersymmetry, actually, we have to do another trick. That is, this chi square is basically quadratic in form. So therefore, I will get some determinant. But you see, when I set this I mean, this is summing over I equal to 2 to n. So there are n minus 2 of them. So you get determinant of that guy to the power n minus 2. But when n to 0, it's actually minus 2. So it's like as if you're integrating out some fermions, because the determinant appears in the numerator. So the idea is you replace this because of this identity, you just replace it as sign. And then, yeah, so then this is the famous Parisi Sourlas action.
Sidebar and side is some grasping.
There's some anti-commuting still.
Is that going close to ending to 0 to do this replacement? Sorry, I missed that.
I'm taking the limit. I'm taking the limit. So minus 2 number of, and we can write down this in the form of like this superspace notation, so that the lowest component is the usual phi, and then we have 1 psi. So and we can write down this action completely in terms of this capital phi, which will be just del phi square plus p of phi. So the supersymmetry will be manifest in this language and so on, and this is the Parisi-Sourlas supersymmetry action. And then the claim is okay. So this is all I wanted to say about this action, but now I think I can go back to
so when
slides.
it's not going to 0, I mean,
Yes.
When it's not on 0 in some sense, there is no, I mean,
Yeah, you can't replace this. This mathematical identity don't have.
This is not valid except for in the straight limit, I guess. Right?
Yes.
And just the replacement of these, the determinant by the sidebar side doesn't apply the, I mean, say, I mean, anything that it's going to be supersymmetric. You have some fermionic degrees in your view, but supersymmetry is much more than, right? So
Yeah, but it turns out this structure is such that I can write down the action, and then I can see that there is this supersymmetry translation, and it is invariant under that action. I mean, we can do the supersymmetry translations, and then we can show that the delta, like if I call this Lagrangian, then the variation is lower. Check.
do you need to prescribe the forms in which the size transform? I mean, is that something that you can?
Yeah. I think yeah, indeed.
Is that something that you sort of demand of the system?
Yes.
So you have fermions and you demand that the action is going to be super.
Exactly. Yes.
So you are. So it's not that these particular symmetries sort of arise in the end Ghosh. I mean, it's not as if
No, it does. It does.
It's
No,
not
yes.
as if that the transformations arise in the end goes to 0, right?
It's an emergent symmetry. It's an emergent symmetry.
Look, it's an emergent symmetry when you propose that the size will transform in a certain way. What I'm saying is when n is not equal to 0,
They don't have size.
Yeah, you don't have size, but there will be fields in the game, the stuff that you have in fields, right? You will have, you have replaced it with something. Does the transformation rules follow from the n goes to zero limit in some sense? Or is there something that you just see in the n equal to zero?
I mean, it follows as in it gets some terms at n going to zero, which allows the transformation of size in a certain sense, which allows for simplifying. The
Yeah, but
terms-
that's sort of, that's in a sense, an input in some sense, right?
So no, you take that action and you check that the supersymmetric already is clear. That's
So at any going to zero, you get the size, you write down this action, and you see that it has a symmetry, which is
No, what I'm saying is that for that, you have to describe the way the side transforms, right?
Yeah,
That's an
that,
input.
that you always do. Let's say, if you wanted to show that this has a, translational invariance, you have to know, how the fields transform in the tableau, right? That you have to put it, right? So, but that's not an input, the Lagrangian has translational invariance, when the fields transform in a particular way.
Yeah, so, right, but that doesn't follow in the n goes to zero limit in some sense.
It
It's
does.
an artifact of the n equal to zero theory, that is what I'm saying.
Yeah, this is n equal to zero.
Yeah, it's not, it doesn't follow from the n goes to, that means, zero limit of what you found. It's an additional thing that you get at the point. Yes. Not when.
Yeah, so the symmetry is only manifest when n
Is exactly strictly equal to zero, right?
well, I don't know strictly equal to zero, taking limits is subtle here,
Yeah,
but
yeah.
probably if you do it super carefully, even in n tending to zero, will emerge. But that may be operating
Yeah.
or you know how to replace it. I don't. Yes.
So
Well-
in the end going to, sorry. In
Well,
the end,
Yeah, I was just going to say that the way I see it, I think you have to take n to zero. I see.
I mean, at any sort of, finite, very small n, this is not something
I-
you would not.
I don't
not be
know how
able
to
get
make
it
sense
from.
of this.
But strictly speaking, in the replica tree, you take n tending to zero. You
Yeah.
don't put n equal to zero. It's not
No,
right.
no, I agree, but
Yeah.
when I'm replacing with this size,
Alright.
actually to write this mathematical identity, I need.
Yeah,
n
yeah,
sticky.
yeah, that's correct. That's correct.
Yeah, but because your,
But I had
the
a
determinant will not have the right form if it's.
I had one more question. So apparently, as you say, of course, there's supersymmetry if I stare at this. But if I just look at the thermodynamic problem at finite temperature at its critical point, what is the consequence of this supersymmetry?
So we can measure like correlation functions and supersymmetry word identity will relate them. And measuring those different correlation functions, we know how they should be related. So
I
that's
see.
the
So you are
check.
saying if you measure a spin-spin correlation versus some more complicated object,
Yes.
complicated object correlation, they'll be related.
They will be relations. And this has been checked.
Okay.
So now I can go back to slides.
go to your slides. Go to your slides, not go back.
And you have to sit it on and everything with. It's too fancy for its own good.
Sorry, before why it starts up. And so to say that, operating and collaborators, solve this problem. And you mentioned something like this time. In this. Problem is solved.
Yeah, I didn't say how it is solved. I just mentioned that. Oh, so when I'm coming here, I'm doing this, I was doing this transformation from phi i's to in terms of phi omega this. Actually, this is not the action you get. This is action you get, you just only write down the relevant terms in the action. But you are throwing away all the irrelevant terms that you generate. But these are irrelevant when d is close to 6. But when you are flowing, there could be some d critical where those becomes relevant. And if that becomes relevant, then there will be extra terms and then the SUSY is lost. And if SUSY is lost, dimensional reduction will not fall.
And that DC is the low critical.
Low critical dimension. Yeah, and according to these people, DC should be something like 4.5 to 5. Between 4 and 5 and roughly 4.5. And yeah, it's also verified because there are simulations that you can do in D equal to 5 that agrees, D equal to 4, it doesn't agree. So it should be in between. So it's a very nice framework that helps you to, yeah. So, but the point is, once you are in this theory where you have this supersymmetry, then the dimensional reduction, this statement is the following, that you take the correlators of operators, which are yeah, so okay, sorry. So there is a problem. The problem is that I was following a thing when I'm usually saying D to D minus 2, but now it's going to be D plus 2 to D. So
Your D's have changed.
So what? Why does? Yeah. So I have this. We have this OSP. So the symmetric group for this is OSP D plus 2/2, and then we consider operators which are singlets of this subgroup OSP 2/2. If you take those operators and if you insert them, and if you insert them in the point when those points are restricted to this subspace, D-dimensional subspace, those correlators will be given exactly by a correlator, which is a correlator of a D-dimensional CFT. And not only that, I mean, why? I mean, of course, if you restrict, I mean, the usual axioms will be followed because there are relations between blocks. But why it is more interesting? It is more interesting because if this theory is local, in the sense like the stress tensor is conserved, then that implies that the stress tensor is also conserved for this theory. That is not possible if you arbitrarily just do some restriction.
My lack of understanding of supersymmetry, but if I just stare at this Lagrangian, which you have written there, how do I see that there's a reduction from D to D minus 2, or say, mean equation D plus 2 to D?
D plus 2 to D. How do I see that? No. You don't see that. You don't see that. Oh, sorry. You don't see that. Yeah. Okay. So no. So there is a way to see. I mean, people have done, of course. So the way to see is the following, that you draw the Feynman diagrams using this Lagrangian. Then Parisi Sourlas showed that there is a one-to-one correspondence between the diagram that you get in this theory and the diagram that you get in the D minus 2 dimensional theory.
It's a one. Say that there is a one-to-one correspondence. Did Parisi have to do some resummation of diagrams?
No.
So it's
all its need is that in the diagram you have to yeah. No, there is a way to see, but not from this Lagrangian.
Okay.
It has to be rewritten in slightly different way. But the crucial point is that to see that, you have to introduce the sources only in this D-dimensional subspace. Then only that will work. So basically what can happen is that you can write down the generating function. You can introduce a fake parameter, say lambda. As lambda goes to 0, it goes to, say, the D minus 2 D-dimensional theory. As lambda goes to 1, it goes to the D plus 2 dimensional theory. Now you have to show that this action, this generating function is independent of lambda. So therefore, you have proved that for that generating function, it doesn't matter whether it's D plus 2 or D, it will always work. To make that work, you have to assume that all the sources are inserted in this subspace.
So you just said something about the stress tensor, right?
Yes.
Yeah. So how do I make sure that this actually the stress tensor is confined in some sense to the D-dimensional subspace?
Yeah. So actually, yeah, indeed. So there are orthogonal terms.
Yeah.
And so indeed, so when you go to this subspace, what will happen is that those operators which are orthogonals, they will decouple. They decouple from the theory. So there is an infinite number of operators which decouples, which don't exist in this dimensionally reduced theory.
But that's something that one really has to sit and do, because it's not obvious that locality in the full higher dimensional theory would actually imply that the lower dimensional theory is.
I mean, when I say that, I mean that if we start with the conservation of E plus two-dimensional theory,
You might be able to project it.
and if I restrict to
Yeah.
these spaces,
Yeah.
And if I look at the singlet part of that,
You
then
also-
I will see that all the extra terms, they are of such types that they will decouple. They decouple. Decouple in the sense their contribution is zero for this conservation.
It's some sort of a projector applied.
It is projector. It is projector, indeed. Yeah, indeed.
Somehow the physical spin operators just live completely in that projected space, and that's why you can do this D minus two factor.
Yeah.
Why is that?
Something like a KK reduction.
Huh?
Is it something like a KK reduction or a KK?
KK reduction.
Yeah, right now it looks very surprising, but there must be a.
So
nice way to see
so actually, yeah, I have a slide on that, like decoupling of this operator. So maybe then we talk about that and we can come back.
The Dropbox is asking this.
And then we can come back to this question again. Yeah. So, okay, so, so
Now the chair is having.
one of the beautiful relation that came out of this program, in my eyes, is this relation that you can see here. I mean, you can write down the D minus two-dimensional blocks in terms of the D-dimensional block. I just took this from their paper. And this was a new relation between blocks. It's beautiful. So now I will explain my motivation behind this work, why I'm interested in this actually. So I do some kind of like I usually work in something called Polyakov bootstrap, and I kind of want to. I'm very much interested in numerically bootstrapping CFTs, getting very precise critical exponents of CFTs that can be bootstrapped, like 3D Zinc model, O2 model, and stuff like that. And this Polyakov bootstrap was not very successful in non-perturbative setup, and it's possible now, because there are such relations between blocks. For example, like this relation tells me that if I know the D minus two-dimensional thing, then I can, if I know the D-dimensional Polyakov blocks, which can allow me to bootstrap non-perturbatively the correlators, then I can also get the D minus two. So that's already useful for numerics, because you don't have to repeatedly compute things for different dimensions. Moreover, there was a relation like this is relating the block in D dimension in terms of the D minus one dimensional block, but this sum is infinite. Okay. This was derived in 2016, and I don't know any important physics problem this has been used or not. It's not no to my knowledge. But this is super important, for example, to make this system non-perturbative, what I just said. Like if you can do the numerical bootstrap, you can do the numerical bootstrap, and you can, like this is like just for a demonstration, like you can get some bounds, like 3D Zinc model is from the single correlator. So just to give you some background on this, like we are taking the 4-point function of the spin field, and then we are varying the dimension of the field, and we are asking that in that OPE of phi, if I have an operator identity, then what is the highest gap that is possible beyond this identity operator? And this is the bound on that. And it is believed that 3D Zinc model is probably very close to this kink. So these sort of things you can play, and you can get more spectrum of 3D Zinc model, which is not seen in the usual other approach of let's say, you know, in the technical language, like derivative functionals and stuff like that. So the thing I do there, actually these relations between blocks is very important. Like that's why I'm kind of obsessed with these relations.
I have two questions. You have one? Yeah, so he goes first.
So basically, you are saying that, you know, for this 3D case, you are using 2D blocks. Is that what? Or
Absolutely. I'm actually using 1D block rather,
1D blocks?
because 2D is like cross of one. Yeah.
But for this disordered,
No, no, no,
So-
not the disorder problem.
This is
I'm going to say why this
So that-
dis-
that's
This
what.
dimension reduction happens with CT, right?
This is the
That-
different problem.
yeah.
I see, okay.
yes.
So that's why.
I will tell
Yeah.
why I'm saying this, but
Yeah,
just a moment.
that was exactly what I was at. First it was the higher dimensional theory has supersymmetry. The lower one, does it have supersymmetry or not? It does. So you are speaking about something where on one hand you have supersymmetric blocks and on the other hand you have non-supersymmetric blocks.
Yes. And
Okay.
this is precisely the supersymmetry.
Okay, but then come to what I was asking is, you have established this for just one example, right? One example of our theory which is here and there. How are you then going to sort of say that this is
But-
like a
but-
general theory?
But this supersymmetry can be just viewed as a group theory problem, and then you can just relate things non-perturbatively between these two dimensions.
Yeah, which is a very deep statement, right? So you are saying anything that has a symmetry of this kind, any field theory that I write down with this is
They will
going to
dimensionally
be
reduce.
dual,
Yeah.
if you will, to something which is a supersymmetric theory which has this as the group is going to be exactly equivalent to another theory which is non-supersymmetric in 2 dimensions more.
Yes.
Is this easy theory?
Yeah, maybe the crucial point is one is talking about critical things, so maybe that fixes things, that's it. So the field theory is fixed with something.
So yeah, at the level of field theory, I don't know much. So, but
Can I answer
I
this
think
question? So first you realize,
Yeah,
first you realize the dualities between the supersymmetric theory and the D minus 2 ordinary CFT. And then you realize that, okay, there must be some relation between superconformal blocks if this relation has to be true. Then
Yes. I
okay,
mean,
then you just check. Then you know the conformal blocks in the supersymmetric theory. You know the conformal blocks in D minus 2 theory. And
No,
then you
but-
just check that this relation exists.
But Apratim, this is also true like at the level of Casimir, right? Like if you restrict to that subspace, you will see that you are getting the D minus 2 dimension.
But first you have to realize that this duality exists, and then you discover this.
right. I mean, what I'm saying is that just by the fact that the conformal group is going to be a lower dimensional, I mean, the D-dimensional conformal group is going to be a lower dimensional subgroup of OSP and D2. That should not be, that's a group theory statement, but what you're saying is much more than that, right?
I mean, I think you
Yes.
have to add this decoupling statement as well, because
Yeah,
you know,
but
have to consider.
I don't know if this is going to be true for all the theories that I write. This is a particular example in which you have checked the Feynman diagrams on both sides and so on and so forth, done some things. But you're trying to pick some particular representations of a larger group, saying that it will fit into a smaller group. It
But
depends crucially on the details of the field theory in some sense.
But at the level of, like, first of all, perturbatively Feynman diagram, we didn't pick any particular type of interaction. Actually, you can choose any, at least any polynomial in phi, and you can show that this agrees.
For this theory, right?
Yeah, but I didn't mention what B is, right?
Yeah, but this is also a class of class of theories.
Yeah.
Class of theories. I mean, for this class, okay, I might buy your argument for this one, but any field theory that you can write down with OSP and B plus 2.
No, this equation is theory independent. For any OSP theory, for any OSP superconformal theory,
Yeah.
this is true.
Maybe
Yeah.
show the next slide.
So this was done in the paper,
Yeah.
independent of theory.
Once it's a statement about conformal blocks like this, it's clear it's independent of theory. Because
Yeah, sure. That's right. If you have this, if one has, but that's extremely surprising.
The previous relation is theory independent. It depends on OSP D plus 1
Yeah.
superconformal.
So it's just the representations organizing themselves in some, unusually beautiful.
Yeah, actually, there is a one-to-one map between the primaries of this theory and the lower dimensions theory. There's a one-to-one map. It's surprising, of course, because it should be infinite in the lower dimensional theory, usually. Which-
Nonetheless, it's relating to critical here. Is that correct?
Yeah.
Plus two
Yeah.
IPs, right? So, okay, so modernly speaking, it may not be that simple. Because it's.
No, I mean,
No, it's just surprising, but it's not the space of all people.
It's a space of all, all the field.
Yeah.
I mean, even that is very large.
Yeah, there is that.
Not large in the same extent.
Yeah.
but even in the conformal field theory, in a sense, it's surprising, right? Because
it's
usually,
very
if you want to write down in terms of some subgroup, then you get infinite primaries for one primary. But here the mapping is 1 to 1.
But at some point, then, but that's still very surprising again. But
Maybe he can give an after dinner.
maybe after dinner.
Okay, so I was trying to motivate that these block relations are very important. So if there is a way to get these relations between block, I think it's worth exploring. That's all my point was.
And
Sorry
this
if I'm
would be
over it.
Equal to 6. Right?
For this particular model.
No, but the relation is ups.
No, this is general.
This is conformal, right? No, but this is some weird type of.
You are talking
This
this
is
D.
not reducible.
This D can be anything.
This D can be anything, right? So, not 6.
No.
Also, it's non-inclusive symmetry. That's all.
Sorry, what is non-unitary?
It was non-unitary because this field phi, it has dimension which is below d minus 2 by 2.
Sorry, below.
D minus 2 by 2.
Also, the fermions don't have spin, right?
Yes.
Yeah, they
So
don't.
there are 6 fermions that are non.
And the super targets.
Shows. So, this version.
Yes.
Okay, so now it comes that okay. So what we studied actually is defects in conformal field theory. So now
Did I understand you correctly that this is therefore a non-unitary CFT?
the higher DCFT is a non-unitary CFT.
When restricted to the subspace,
It becomes a unitary
Yeah,
CFT in the lower dimension. Yes.
Yeah, because Ising CFT is right?
So we are interested in defects in conformal field theory, and we want to understand like how this sort of dimensional reduction works here. And as I said, like so one question is obviously Parisi Sourlas supersymmetry, whether this support this kind of extended objects. And naturally, like physical systems will have some surface and all. So therefore, whether it exists in this defect setup is important. And also, this is a way to study some sort of a non-unitary CFT. Of course, its structure is very much fixed, but still we are studying some non-unitary CFT, which is beyond like bootstrap paradigm. So that's also why it's interesting. And moreover, nowadays, like very recently, for example, like there was a study on defect bootstrapping, where they can kind of find a very close to like island-like picture, which we have seen for easing model. So now like non-perturbative bootstrap can be done for like non-trivial defects, for line defects and things like that. There are some restrictions, but that makes my point is that now it's important that we try to understand all the relations between the blocks in the defect case. And one of the byproduct of studying this sort of duality is that you get like so many relations between blocks that you will be surprised that there exist so many relations, and it's trivial to derive them if you are using this sort of supersymmetry argument.
You would understand, if we take the so in the bootstrap, we take the lower dimensional
Yes.
bosonic theory into play. There you would have an unitarity footage, right?
Yes.
But somehow the combination of stuff that you have on the right side, which makes up the higher dimensional block, makes the higher dimensional block non-unitary. Do we understand how this works, in the sense that how the unitarity goes away?
And violates the unitary boundaries.
Yeah.
The
lower dimensional ones are
unitary because for like exactly for the reason, because since you are restricting to singlets of OSP 2/2, you don't see this type of fermions that Anthony was mentioning. And also the bound I talked about, like this is below d-2, but but that when you go to the lower dimension, that is consistent with the unitarity bound of the lower dimension. So from the lower dimension point of view, this is unitary. But as you go to the 2 dimension higher, then it's below the unitarity bound.
So one question, when we say defects in conformal field theory, if I just go back to the lattice model at its critical point, so you're trying to draw some domain walls and looking at its correlation functions. Is that?
So to do what? Sorry.
So you said defects in conformal field theory.
Yes, yes.
Right. So in this language, you're just looking at.
Yeah. So let's say one trivial thing would be that, let's say if I have surface and I can't ignore the surface effects, then that's like a defect, right? Because I can have a boundary CFT there. And that can act like that. But moreover,
that's like a domain, right?
Yeah.
Because the domain also.
Yeah. Indeed, I think, yeah, that's right. And also, like, I can switch on, say, a constant magnetic field in certain direction to break the symmetry in certain direction. So that will act like some line defect or some higher dimensional defect.
But when you switch on a magnetic field, you switch it on throughout the lattice or in some.
In one direction, let's say.
Oh, in
In one direction. So like one such type of defect, like magnetic line defect, is nowadays people are studying. Like the plot I was showing is actually in that context. Okay, so it seems like this is the right time to do this sort of study, and it's also 50th year from the first paper on this subject. So this is a nice time to, I think, explore this topic in the context of defect. So defect, it breaks the full conformal group. So you go from SOD plus 1, 1 to, so defects are leveled by these two guys, P, Q. So P is the dimension of the defect, and Q is the D minus P, that's the co-dimension of the defect. So we are leveling them as by these two numbers, and the full, and on the defect, the symmetry breaks down to this group. This is the full conformal group on the p-dimensional subspace. Times it sees the the defect operators are charged under the rotations around the defect, which gives you this SOQ group. And in a defect CFT, there are two class of operators. Like you have the bulk spectrum and you have the defect spectrum. So bulk spectrum, I mean, they are leveled by the usual delta, the dimension and the spin, and their OP relations is unchanged. I mean, it's just like the usual. If it's just the same as when the defect was not there, and the defect operators are leveled by the quantum numbers under this SOP plus 1, 1, and also the transverse spin which comes because of this SOP. Importantly, you can now also quantize your Hilbert space around some point on the defect. So what you can do is that you can expand any bulk operators in terms of the primary and descendants on the defect. So that gives you a new like bulk to defect OP coefficient, which is a new OP data, and that's important. So that's just roughly what defect is. But you can see that the situation is a bit confusing here, because immediately you realize that what does it mean to, like, so now, okay, so I will tell about the exact random field model that might flow to some defect CFT, which will realize this type of supersymmetry towards the end, because that work is an ongoing work. But in this paper, we see it more from the point of view, like if I have the supersymmetry, then what type of like what's the picture, like what do we need, and what will be the conditions so that the dimensional D+2 theory will reduce to D-dimensional theory in presence of the defect. And you can see that the picture is a bit confusing now, because now you can say so this p-dimensional defect, there is a CFT on it, so therefore it's a CFT on its own. So I can just uplift this the CFT on this parallel space, or I can uplift the CFT which is living on the bulk, keeping the p-dimensional defect untouched. So therefore, seems like there are two types of uplift which is possible. One is of dimensionality p+2, and the other is of dimensionality p. Nevertheless,
Sorry, p+1 and p+1.
1 and 1.
1 and 1. No, that will not work essentially. because of this supersymmetry, you have to extend it by two bosonic direction, and then you introduce two fermionic degrees of freedom.
Achha, you want to.
You can ask this question even in the usual case, right? Why it was not one dimension?
Okay, I see. Like, yeah, either of the CFTs, you have to live by two.
Yes,
So that's why-
yes.
Okay.
But the surprising thing is that they are defects of different dimensionality, but somehow they should be reduced to the same defect, like P comma Q theory. Yes.
So this map that this is the both point.
Yeah. That's actually one of the things that we are trying to say, that either you can reduce or you can also uplift. It's not completely proven that you can uplift everything, because there are operators which are zero on this theory. How to reconstruct them is an open question. But when there exists a map between the operators between here and here, those you can reconstruct. The correlators of those you can reconstruct. Okay, so this is a surprising fact, and actually the answer is that both of them are possible, and both of them will reduce to the same defect theory. So there are two uplifts in this case. One is this parallel space uplift, as I said. So the prescription is very simple. You just take your parallel direction, you uplift it by adding two bosonic directions, and if you think in terms of the superspace, then you have two fermionic, basically Grassmann, they are anti-commuting scalars. So you add those two directions. And for the perpendicular space, the transverse space, they are kept fixed. So what you are doing is that you have a P comma Q theory. Now you are going to a P plus 2 comma Q theory. So you can see the symmetry preserved by doing this will be of, on the defect, they will be of this kind, OSP P plus 3, because it's a P plus 2 dimensional theory. So P plus 3 comma 1 slash 2 times the SOQ. So SOQ is unchanged. That is the same. And this corresponds. And you should see this as simply like this is a PS uplift of the usual CFT, because the usual CFT, it was exactly same as if you have a P plus, you have a P dimensional theory, you are just uplifting the CFT to P plus 2 dimension. That's it. And that's what.
So that's why this is, both these things would be like a trivial. Is that right? I mean, there's no new information coming out of this. I don't see how you know what I mean, right? You have
no, I will come to that.
Unless there's some interaction between the defect CFT and the bulk CFT.
No, I mean, there is this BOE, right? The bulk to defect BOEs, which I was showing. So there is a link.
But
But-
tell us what happens to that.
No, I mean, they will be mapped to, okay, so let's go and we'll show like when this dimensional
Can I
interaction.
ask a question? The space-time dimension of a PQ defect is like P minus Q. Is that correct?
D is P plus Q.
This P plus Q.
Yes.
I'm sorry.
Yeah, so, right. But the point is like, even the whole CFT, you can just think in terms of the defect Hilbert space. So in that, even if you have interaction, but you can expand all the modes in terms of the defect modes, and then you can think of them like studying some CFT. So there, I would say that it's the usual Parisi Sourlas type of uplift that one can think of it that way. And in the other case where you.
Yeah, let me ask sorry, so, for instance, this initial D plus 2 to D, give you this interesting relationship within conformal blocks, right? So do you expect to retrieve any further information by doing this defect thing?
We will get the relation between the blocks of the defect, which are different.
Blocks of the defect.
Yes.
Blocks of the defect CFT.
Yes, defect CFT. That's the goal. That's what I was trying to motivate. So this picture is where you keep the dimension of the defect fixed, but you uplift the transverse direction. So that's what you do. It's just the same. The role is reversed. So you go from a P comma Q theory to P comma Q plus 2 theory. Now the symmetry preserved by this defect is SOP plus 1 comma 1. So this is the usual one. So it's true for both the original theory and the uplifted theory. But now they are charged under this global symmetry, which is OSP Q plus 2/2. So for example, like if you take a representation of this and decompose them in terms of SOQ plus 2 spin, then you have a operator of spin S, you have an operator of spin S minus 2 and two operator of spin S minus 1. These two are fermionics and these two are bosonic, but all of these operators have the same scaling dimension. So this is very different from the usual Parisi-Sourlas type of uplift. So in the usual Parisi-Sourlas uplift, the different components that you have seen, they have different dimension. So you see this particular, but nevertheless, we are claiming that this theory should map to the original theory. So how is that possible? So what we are saying is that in TSU picture, the transverse space uplift picture, the defect operators are charged under OSP Q plus 2/2. But in the dimensionally reduced theory, they are only charged under OP. So why it is possible that these two theories are give the same result? And notice this is not the usual Parisi-Sourlas symmetry. In fact, it commutes with the usual Parisi-Sourlas generator. So it's a different reduction in the global symmetry that is happening here.
Sorry, another question. So I thought your previous argument when you were considering the standard size picture, you said that if you think of the spin operators in this T plus Q dimensional theory, there's a way to rewrite everything to show that it just projects onto that effective D dimensional thing and the rest of the two directions are the forbidden.
Yeah. We will project at the end of the day, we will consider only operators which will be projected to the spins which are of the reduced dimension.
So, but then why should I think of it as a duality?
I mean, it depends what you mean by duality. I mean, all I am saying that the correlation, I'm saying that the correlation function of operators of these two theories are same. This is the statement.
For a class of
For a class of operators, what class of operators? For those operators which are singlets under this OSP 2/2 theory. Yes. So indeed, and then actually the non-trivial question here is that can we recover the information about OSP 2/2 charged operator in the uplifted theory? And that's an open question. We don't know. So we were initially surprised like why this is happening, and then we found out that in the literature actually people have already studied this type of theories and showed that they actually just independent study where they consider a theory and it has a symmetry, let's say OSP m/n, that gets mapped to OM minus n. If you consider let's say if you take the Lagrangian like this, it's in D dimension. So if you do it around D equal to 4 minus epsilon, and if you compute the fixed point or anomalous dimension or things like that, they will match exactly with the usual 4 minus epsilon theory that we will consider, except that this will be mapped to a OM minus n theory. So yeah, that's the relation. So that actually exists, and we didn't know. So this is a new component it's a map between global symmetries. Yeah. In same dimension. This mapping is in the same dimension. And this is due to the TSU picture because that said that the dimension of the defect is same, but they are charged under two different global symmetry. But still they give you the same correlation.
This OSP transaction is it compact or it's non-compact? Because O is compact, right? So there are no natural basis.
I mean, do you mean like should it be SOQ? Sorry,
I'm
repeat.
just asking. I think the answer is no, but I'm asking if the OSP is not compact.
OSP is not compact. Yeah, sure. But that was true even for like any OSP.
Yeah. No, I'm saying it's surprising that the compact suite and not the non-compact.
Yeah.
Representation theory, it's very simple.
I would see that would be a restriction.
Yeah.
Such sector of the
Projection of some sort of this.
But you know, how about like conditions like meta-IT representations into somewhere?
And they don't, right? So the higher diet is not limited, but the lower dimension one is. to, picking some sector which is as probably into the sector. So, very clearly.
Correlation
I
functions
think
of
there is a
charge.
theorem that, so, non-compact, then, you cannot have finite dimensional Murray representations.
Yeah.
Anyways, the, condition.
Although, I should say that all the check we did, actually, we were just computing some correlation function and checking like whether they have the same anomalous dimension. Those type of checks we did. So we still put this as a conjecture because people who studied this sort of reduction in different contexts, like they do it example by example, they never say that this is true in general. But our transverse space uplift seems like saying that there is a way to see that it should be same when you put this restriction. So, okay, so there was these two type.
20 minutes. 20 minutes.
20 minutes. Yeah, that's good. Okay, so these are the two types of uplifts that's possible, and this is a new type of reduction that we found, and then this is, I think this is the part where I was trying to say that there is an infinite number of operators which is decoupled, and it's simply because of the fact that suppose I consider a correlator, and in that correlator, I place all the operators only in this d-dimensional subspace. And let's say I have a correlator which is charged under this OSP2/2. Then I on the right hand side, like to express the correlator, I need something which will which I need to contract that metric of 2/2 direction, right? But I have nothing, because all the direction, like we have only X, which are a component of this RT, but that if you dot product with that with G2/2, that's 0. And if you just take the trace of G2/2, that's also 0. So the claim is that all these operators, the correlators of all these operators with any operator that we are choosing, they are all 0. So therefore, they decouple. One such operator, as an example, is something like this. Like if you have some indices A and B and you are contracting with this operator must be decoupled because of this reason. Because the but like what we can do, we can measure correlation functions. So let's compute all the correlation functions restricted to this subspace. You will see that all correlation functions are 0. So that's what we mean by there is an infinite number of operators which gets decoupled, and it's very crucial that this happens, and that is why this whole matching is happening.
And in this correlator, you are restricted to the subspace. Is that?
Yes. Yeah. We have to, but otherwise we will have some coordinates where we can, like we have some theta coordinates, and then I can.
Yeah. So, but if you exit the subspace, 1 point on the subspace and 1 point, outside, those will be non-zero.
Yeah. If you have any component which is not on that subspace, then you have non-zero.
But that means, there's something between, this CFP and, whatever is happening outside the subspace. Here is not decoupled company.
Decoupled.
In the usual sense of decoupling, we would say that, this operator said and that operator said all correlations vanish. But, if there is one leg on the subspace and one leg outside,
yeah,
then it's non-zero.
Okay, yeah.
Then would you say it's a proper decoupling?
I mean, yeah, I think at the moment I don't have a good answer to this, but
the group theory might work. That's what they say. This probably decoupling, but
I can clearly see that if you do that, what you are suggesting, then it's not zero.
not
So
but if the something doesn't go, group theory also that does not work. Because they already built that and
representations which have and mix of both sides. So it's sort of closed subgroup.
not very clear for me. I mean, what is that? There's some magic happening at the representation theory.
Then it has to work there.
this is more important, like, the correlation functions is not just fruitful, right?
No, but
For instance, the data is present in correlation. Right? The data can be known.
So you're talking about correlation functions of charged operators,
Right.
which are not.
Yeah,
Right.
there this will not
So,
work.
yeah, they don't dimensionally reduce.
Right, right.
But the original argument was not for these operators,
Yeah.
right? It was for discrete correlations or whatever which were singlets. This time.
The magic is, if you look
All
at,
for the single set.
yes, there,
Yeah,
those
yeah,
operators deduct.
yeah, these are singlets opposite. Only for that.
No, but then what is the meaning of that's what I'm, so meaning of what, decouple, I would mean that both the legs are, one leg here and the other leg elsewhere. That's it. That is what
I
it
would
says
say
decoupling.
They're zero in the OP of the good sector.
Ah, okay.
There is
There
a
is
sort of
sense
subset of, operators which are closed and that particular thing, obeys the lower dimensional.
and the and the lower dimensional CFT is completely fixed without those
But there are, the whole.
Of course, of
whole
course.
theory things do drop, of course, because this is a larger group, right? There will be
that's yes.
subgroups.
in fact whole set. Yeah, so that's why the uplift is non-trivial. Saying anything about uplift is non-trivial because in this side actually things are zero. Many things are zero. Like all these things are
Yeah, I
zero.
mean, of course, there is
So-
always harder to call.
So okay, so they now that there are these two sets of thing, we can now ask for this type of block relations, but in the context of defect. So I will not actually show many such relations because they are just relations, but we found many relations for them, and the method that we use is the following, that so, if given a super primary, we can construct like just primary operators by taking derivatives with respect to theta theta bar, and this is also some derivative with respect to x and theta theta bar. So what we can do is that we can consider, let's say, some correlation function in the higher dimensional theory, the uplifted theory, and we can act with this some differential operator, which we construct. Then the claim is that when we so this way we can find like different correlators, right? Because for example, if we have an operator like this, I can act it on the correlator of 2-point function and get the correlation function of these two primaries. So these sort of things can happen. And moreover, we know that for 2-point function in the bulk, let's say in the context of defect, the 2-point function is completely fixed in terms of an arbitrary function of two cross ratios. And these are the cross ratios in terms of the y variable. It's in the superspace. So this is completely fixed. And now we want to say that you can kind of like when you act with the derivative, you can pass through and write down things in terms of this UV coordinate, so that and finally you want to set finally you want to set this theta theta bar coordinates to 0. So actually you can write down everything in terms of the lower UV. So there's like small UV. So small UV is nothing but the same UV, you have set theta theta bar to be 0. So then you get a relation between the correlation functions. So this is some correlator of the let's say phi, and then you are acting with the differential operator on that to get the correlator of some other operator. There's just some relation that you can look out. And then the idea is that since it's a correlator of the higher dimensional theory, so you should be able to expand them in terms of the higher dimensional block. On the other hand, because of the dimensional reduction, it tells me that this I can still expand in terms of the lower dimensional block. So therefore, there should exist a relation between the derivatives of the lower dimensional block in terms of the high dimensional block. And this derivative can be also 1 in the sense like you take literally the operator itself. In that case, you get a relation between the blocks between those D and D plus 2 dimension. but you also get the relations between derivative of the blocks in terms of the blocks of d plus 2 dimension.
So why are there 4 primary instead of 5 division relation?
4 primaries. Sorry. Here, so where you had 5?
Like the second slide, 5 blocks.
Best relation that we showed initially. thought development. Or else, no, I don't remember.
That one at 5 components of various things and branches.
Yeah, so this, it's possible if you have spin. Actually, sorry, I was thinking about, yeah, so if you have spin, you can have something like this, which you will not have. Yeah. So, sorry, yeah, I'm talking about the correlator of scalar operator. And then you have basically these components. And that's what you will get. So you will get some relation which looks like this, like it acts on the P comma Q theory block, and it gives you some finite term relations. These are fixed in terms of the supersymmetry. And so you get something which is for bulk channel, you get something for the defect channel, and you get for both the uplifts. So there are many relations, like we derived all this. And so this was fun. But then you can ask, is there any reason that there is this parallel, and like there are 2 sets of operators? Are there some relations between them that can explain, like I can go from one to the other? And actually it turns out yes. So this actually not been explored much, but it was mentioned in one of the paper by Eduardo and some other people, actually including Emilio, but it was not explored well. And the point is that you can take the defect CFT and you can think like sort of analytically continuing from P plus 1,1 to SOP plus 2. If you do that, then actually you see you can swap between Q and P plus 2. And under that swapping, you don't know, like, so this seems like things should have some kinematical identities under this swap. And this is the map. So we give the full map, how you should map between operators and defect operators and so on. So this is the metric of parallel and metric of transverse. And if you swap, we find out that under this map, actually, if we have this, we can get this. So all the relations we derived can be derived for this one as well under that map. So this was something that we found, and
then the map between what and what?
The defect operators.
The defect operators
The
of
spin and delta.
Okay.
Yeah.
The 2 uplifted. The 2 uplifted.
This is true for any defect. This has nothing to do with that, but we found that this explains why we have these thrust separations. And then we found this nice relations between blocks, which relates from like the bulk block has this nice relation. Sorry, this should be G comma U, but and then you can use this. Actually, we found that, for example, for Q equal to P plus 2 is a special point, you can see. And then basically you can use that, like, for example, if P equal to 0, then Q equal to 2. So that explains why Q equal to 2 blocks can be written down, because P equal to 0 is the usual block. So if you know the usual block, then you can write down the Q equal to 2 block. And you can use this for other things, like you can get things and so on. And then we repeat this exercise for other kind of observables. We try to get as much possible out of this thing. And then just to mention, like so for example, we looked at some correlator like this, and we find a relation for Apple functions, which seems like a new relations. I tried to find it in literature. It seems there is no such identities known. So, and actually there's an important application of this, but let me not.
Describe the 3-point bulk.
Yeah, the block will be the Apple function times second bulk. So it's a piece of it. And by acting this differential operator, you can You can find many relations, but some of them I found that already known in the literature. Then I found one which is not. And this is important for some reason, but which I should not explain here. Okay. And how much time?
6 minutes, 5.
Okay, yeah, I'm kind of like, yeah, I don't need so much time actually. So finally, I just wanted to say like, so now we take this proposal quite seriously, for example, and then what we claim is that you can take the like Lagrangian which describe this minimal models, and then those has some critical dimension, and you can think of them as a flow, but you can use this Lagrangian literally because they are strongly coupled. So to solve these minimal models, of course, you use the constraints from Virasoro symmetry, not this Lagrangian. But since it has a Lagrangian, I know how to uplift it. So I can get the 4-dimensional minimal models, if you want to call it. And you can construct the whole set of correlators using the prescription that we are using. So they are correlators in the 4th dimension. They have the conserved charges. The question is there an explanation of like why there are these charges? Are there some sort of integrability behind this, which we can expect in this d = 4 dimension? So we don't answer that, but we do this and pose it as a thing to think about, that if we can define some sort of a integrable theory in 4 dimension using this sort of map. Which
theory, I mean, the higher dimensional one would only be an integral subset, right?
Yes, using this prescription, getting that subsector is very easy because you use this map and
there is no reason to expect that the whole theory is going to be integrated. Because it's first
it's yeah.
And
yeah, we don't know, but let's say, can we solve that part of the theory using this information? Because we know a large chunk of information about this.
But only for that subset.
Yeah, I agree. But let's say we know all the OPs and things between those operators. Now let's take the correlator with that operator with the other operator. Can we use some bootstrap-like thing to get
sure, but you never have integral, right? Because it's a non-unitary theory.
What is, because there are non-unitary minimal models. Anyway, I don't want to claim anything serious, but there's this cute thing that one can do. And finally, talking about like literally a random field model, which will perhaps have this type of supersymmetry realized in the fixed point. So this is some ongoing work, and one should not trust it completely because we are still doing it. But we found this result, like if you consider some, so this is a Lagrangian which you can arrive with a term like a fixed magnetic term in the lattice picture. You are just adding a fixed magnetic term, which will show up in this form in the continuum description. And then the question is, does this model flow to the SUSY model? And usual answer is yes. We find the same critical exponent and so on to the order we can compute. And then we compute the terms that we are ignoring in the derivation. So this is like one such operators which we ignored. And we found that it has a positive anomalous dimension. Also, we computed this operator, which has also positive anomalous dimension. So therefore, since the anomalous dimensions are positive, it seems like they can never be relevant, no matter which dimension you do this. So therefore, it seems like as long as the bulk theory gets dimensionally reduced, this particular defect, it's called pinning defect, it will also reduce. That's the picture we have currently. So just to remind, like there is a Gaussian fixed point in the all dimension, and then around 6 dimension, there is another fixed point, which is this Ising fixed point, random fit Ising fixed point. And then around d = 4.5, you have a non-SUSY fixed point. So that's the picture of the bulk theory. So therefore, we expect that up to this point, the pinning defect should also dimensionally reduced. And then, of course, the question would be, what about the boundaries? Do they always dimensionally reduce too? Then, of course, as I said, that they relate different blocks. Actually, you can also use this to derive relation between Witten diagram and so on. So you can ask the PSUC in crowd background if they give some non-trivial identities between amplitudes. And you can ask, of course, that if we simulate that model we are proposing, then can we see the dimensional reduction directly in this spinning defect kind of model? So we are thinking about talking about that with some people, but we don't, yeah, that's something that's ongoing, all of these things. So yeah, that's all I wanted to say. So that's the picture. So you have some defect with the random field model, and that flows to the Parisi Sourlas fixed point, and then that reduced to the CFTD with defect. This uplift is a question about that whether there is, we can uplift the sector as you mentioned, but can we do something to construct the whole theory? Is it possible? Because that will be very interesting. But that's for, yeah, that's all I want to say.
Sojik?
So going back to the statement that you made, you said that there's some work where in 4 dimensions they didn't see this Suzy critical point, but in 5 dimensions they saw when they did some simulations.
Some Monte Carlo
Yes,
simulation.
what exactly did they see in the simulations which told them that there is Suzy there and
Because d equal to 4, if there is a dimensional reduction, then it should map to the d equal to 2 Ising model, which we know exactly. Yes.
But there must be some more refined observables which tell you that there is Suzy there and Suzy.
Yes, you can also compute the correlator. Then you will find that in 5 dimension it matches, but in 4 it doesn't. But I know in 5D they showed that it matches. I don't know if they showed it in 4D that they don't match. I said that if there is a Suzy, then there are different correlators which gets related due to identity.
Okay. So like spin correlators are related to some other correlators.
Yes.
So can you tell me what those other correlators, if you remember?
No, I don't know in terms of the spin variables, but what I was saying is that, for example, in this Suzy language, like the correlator of, let's say, 5555, which is this guy, and if I compute, let's say, something like psi bar psi 55, these correlators are constant. If I know this, I also know this.
Somehow one has to translate.
Yeah, one has to translate.
Maybe I can.
Yeah, maybe.
So it's how you take the disorder averaging. So you can take a disorder averaging of the full 5555, the disorder theory, take the disorder average, or you take the disorder averaging, take the 2-point function disorder average and then take the product. Disorder average 2-point function, and then take the product, which is like a 4-point function. And
so that sounds like a replica.
Yeah. So compare that with the disorder average 4-point function. That's they have a relation.
Can you see?
If you say Suzy, then they're related.
Is that what people are numerically?
Other questions?
So that's the experiment. So this duality works only when the higher dimensional counterpart has a disorder.
No. So these are two different pictures. One is that you have a disorder with the random field. Now the question is whether that flows to the fixed point which has the Suzy. If it has, then there is a dimensional reduction for the sector, like the prescription we say. So the theory at the Suzy point, I mean, there is no disorder, there's nothing, it's just some fixed point. Yeah.
Can any random two-dimensional field theory or and just two-dimensional doesn't work, I guess. But
No. This kinematically it works in any dimension. This Suzy structure works.
So can you take, I mean, input any two-dimensional theory and get some you were saying that the uplift is of course problem.
Yeah.
But if I started with a movie theory or something like that.
Leuven theory.
Yeah.
You can uplift, but all these singlets.
Yeah, I'm only saying.
Yeah.
I mean, I have people play sides. Try to plug in
For the minimal models, Emilio wrote a paper on this, but
Yeah.
we also did here for the boundaries.
Yeah,
but-
Boolean theory would be a very natural thing. It's, closed form blocks, etc. And lots and lots of interesting things there.
Well, I mean, if you just take those blocks and, compute the high dimensional block, I in the one, and then try to guess if there is a theory, but
Yeah, I think that
Yeah,
that's
that's
not
fun game to do.
yeah.
I also, I think like, since these are kinematical, whether this also tells some relation between amplitude, say if you do it on a celestial sphere or something, what happens? So that will be also interesting, I think. That might give some non-trivial relation between d equal to 4 and d equal to 2, so that.
If you have no other questions, let's end the session and let's at least